Hello, everyone. My name is Cole Jenkins. I'm this year's suspension lead. And today I'm just going to go over a basic overview just to scratch the surface a little bit on what suspension is, what it's about. Yeah. Okay. So basic overview, I'm going to go over the team, who we are, what we do, talk about the purpose of suspension, types of suspension, some components we have on the suspension system. I'm also going to talk a little bit about dynamics. So essentially, suspension is broken down into like two main groups. There's the dynamics portion, and then there's structures. So dynamics is more like how the car acts, how we design our components for the car to act. And then structures is designing said parts so that they don't fail under certain boundary conditions that we see on the car. Then I'm going to talk about at the end a little bit of stuff that we can see in testing and validation. All right, so the team, who we are, we're just a bunch of students, just like you guys. We are in no way any different than you guys, so there's no reason to feel kind of nervous around us, like we're not any different. A lot of you are probably smarter than us, actually, so it's good that you guys are here to help us out, to help join the team, because you can bring a lot of good ideas to us and help us solve a lot of problems and make the car go fast. So we're just a bunch of engineers trying to learn. A lot of mistakes along the way. So a good way to learn is to join this team. All right, so overview of the system. So what does suspension do? Suspension connects the road to the car through the tires. So everything between the road and the car is our responsibility, really. Controls the car over bumps and maintains ride quality. It also, the main goal is to control the tire and the loading of the tire. This is because in racing, is by far the most important thing to be able to control the tire and maximize the grip out of the tire, because more grip means faster lap times. All right, so just some basic types of suspension at the bottom there. So our car uses a form of the double wishbone suspension. If you've seen the car, it kind of looks the most like that. It uses a version called the SLA, which is short long arm. It just means the control arm lengths are different. And we do that to help control camber through bump, which camber, if you're unaware, is if you're looking straight at the car, it is the tilt of the tire this way or that way. And camber changes with vertical movement of the suspension. So what that means is we can control the camber better when the suspension moves up or down. All right, so suspension components. We have control arms, which are these carbon pieces there. They basically connect where the wheel is to the chassis. We have push and pull rods, which is this section here. It's hard to see, it's behind the tire, but it connects to the bell crank and then to the upright. We have our hubs, which is the actual rotating part that the tire attaches to, or the wheel attaches to. It's the part that pulls the wheel onto the car. And then we have our rocker arms, is what some people call it, but we call them bell cranks. That is this part here. That connects to our damper and the push/pull rod, like I said. We also have a steering rack, which is pretty self-explanatory. It's what, when you turn the steering wheel, it's what turns the wheels of the car. And then there's the chassis, which it's not really a suspension component, but it depends a lot on the suspension, how the suspension performs. If you're interested in chassis, talk to Jason. He's here. So some more components. Yeah, lots of cool stuff. So this is basically an exploded view of what we call a corner assembly. So we call a corner, like there's 4 corners on the car, and the corner basically encapsulates what the wheel is attached to before it goes through the control arms to the chassis. So we have our hub, brake rotor, and brake caliper. different bearings, and then we have our upright, which holds the hub, and then we have, then the upright connects to the chassis via the control arms. And this is our rear upright, by the way. The only difference being that we have a tripod race here and larger bearings because the rear of the car is where the drive wheels are, so it needs to be much stronger and designed slightly differently because that's where the power comes from the engine. So, all right, so to talk a little bit about dynamics, this is like a huge thing. So there's thousands of different things you can change on the car, and it'll affect the way the car drives many different ways. So you think about it, we're given a tire and there's 6 degrees of freedom in space, and we have to pick some way to constrain that tire. So there's a lot of different ways to do that. So if you're interested in math and physics and stuff like this, the dynamics is really cool behind it. There's a lot that goes on, a lot of projects you can work on there. So like I was saying, tires are the most important part of the car, really, because all the forces travel through the tires. So we're basically, with tires, we're concerned about grip, because without grip, you're just sliding around, and the grip is what, if we can increase grip, that's the easiest way to make the car go faster. And the way we do well in this competition is by gaining points. So if we make the car go faster, we gain more points. So grip really is a function of like the tire size, different tire compounds, rim sizing, slip angle and ratio, vertical load, temperature, pressure, and camber. Those are all basically really important things we look at with the tires. So Formula SAE is unique in its own way that we have like multiple different tires we can choose. We're not, for instance, in Formula One, they all really have to use the same tire. They have the 3 different compounds, but they have to use the same ones. So in Formula SAE, we can kind of choose what tire we want to use. So there's a lot of validation that goes into that, like why we choose this tire. So we can do a lot of analysis on the data from tires. So there's a company called Calspan that tests these tires, like all the tires that most Formula teams use, in a very controlled manner, and they get all this data. And then from that, we can kind of look at these tire outputs of slip angle versus lateral force, lateral load, or vertical load and lateral load, quartering stiffness, self-lining torque, and pneumatic trail, and a bunch of other stuff like that. So what that kind of looks like is we have these tire plots here with different tires tested. And then this is just an example of a plot of slip angle versus lateral load. And from these plots, we can kind of make a better decision on what kind of tire we want to choose on the car. And this is just kind of a cool, they used to do this back in F1, back a while ago. They put thermal camera on the car and you can kind of see the tires heat up in different spots. Does anyone know why the inside of the tire seems to be getting hot just in the straight line? Any ideas? Yeah, exactly. So camber, the tires are tilted in a little bit, so that part of the tire is really contacting the road a lot more in the straight line. So, and then you can see in the corners, the whole tire heats up a lot, the whole contact patch of the tire. All right, so load transfer. This is just another important thing we look at when designing the car. So load transfer can happen laterally, which is side to side, if you can see by the car. So we call x-axis out the front of the car, y-axis out the side, z-axis out the top. Kind of think about it like an airplane, basically an airplane, but upside down, right? So we have roll, which is rolling about the x-axis. Pitch is rolling about the y-axis, and yaw is rolling about the z-axis. So lateral load transfer happens about the y-axis. So you roll like this when you're turning, and longitudinal happens when you're braking. So you go frontwards or backwards, like accelerating or braking. So that's mainly a function of the footprint of the car, and what I mean by that is the track width and the wheelbase, so how wide the car is and how long the car is, and the center of gravity height, which is how high the center of gravity is off the car. So there's a lot of different geometric things we can change to help this, as well as kinematic things. It matters because we want the car to be somewhat normalized. So if you have a whole lot of weight transfer, then the grip is changing a lot on each tire. So if you have a lot of weight on one tire, that increases the grip. So we kind of want the car to be stable in a way, so we don't have a lot of weight transfer. We can control it, like I said, by changing the footprint of the car or adjusting damper settings and stuff like that. Yeah. All right, so kinematics. These are pretty much the constraints that control the suspension movement and force transmission in the suspension to the tires. So there's all these parameters here that we pick when we're doing our kinematic analysis and picking those points in space where we want the tire to sit. So there's things like kingpin inclination angle, which is kind of like camber you can think of, but it's not the same thing. It's like the angle of the steering axis almost from this view. We have mechanical trail. We have our steering geometry that changes a lot of stuff. And we have scrub radius and camber gain. So these are all things you could talk about this stuff for hours. And there's a lot of stuff in depth here. So if you want to learn more, just keep coming to suspension, start reading stuff, and there's a whole lot to learn about this. So all that stuff controls how the car moves, how the wheel moves. And then there's what we call a roll center, a pitch center, and there's also a geometry called an anti-dive and anti-squat that also affects how the car moves. So this is just kind of a picture of some kinematic design stuff. Like I was saying, when I mentioned like points in space, this is what I mean. Basically pick where all the control arms are going to connect and stuff like that. And as I was saying, all those parameters affect, we pick those parameters, and then we can make a model like this to figure out where everything is going to be in space. So we also have to worry about damping on the car. So this is just a short video of showing, I guess, how dampers would work on a regular car. So on our car, we also have dampers. It's not like a go-kart where there's just no real springs or anything. So we can adjust our dampers based on event, or we can tune them based on different events. Like for instance, in acceleration, we want a lot of weight transfer rearward, but we don't want the front wheels to lift off the ground. So we can adjust our dampers accordingly there. Again, talk for hours about damping and dampers. Some really interesting stuff there as well. All right, so now I'm going to go into some of the structure stuff, the other half of suspension. So some goals with structures. So we want stuff to be as stiff as possible and pretty strong. We don't want stuff to fail, but we also don't want stuff to be really heavy because we're building a race car here. And the more weight you add to the car, the slower it's going to be, essentially. So to do this, we will do some basic hand calculations initially, based on some mechanics and materials concepts. And then we utilize an FEA software, which is finite element analysis. We use ANSYS. So ANSYS can allow us to analyze the stresses and strains seen in our parts to ensure they're not going to fail under the load cases that we see on the car. So another important thing with structures is we want stuff to move as it's intended to move. So when you're looking at something in like CAD, you think it's just like a solid, like it's infinitely stiff. That's not actually true. So stuff does move around, stuff deflects. So that's another important thing to take into account when designing your structure. So, and this kind of deflection and stuff moving around can also change the kinematics as well. So that's another important thing to take into account there. All right, so just some quick stuff about validation. So we do run the track and test. So the way that we can validate and kind of test and tune our suspension is through driver feedback. So the driver can say, "Oh, I'm oversteering a lot, I'm understeering a lot," then we can kind of try to change some stuff to fix that. We can also look at our data and kind of see what the car is doing as well, and it should somewhat match up to what the driver is saying if the driver is good. So, but that's an if there. Yeah, so we do a lot of data analysis. We kind of compare our data to our modeling. So we have a lot of modeling with our kinematics to choose our kinematics. So we kind of try to compare that to our data to see if what we design is actually what's happening on the car, because sometimes that's not always the case. And we also do tracking of our setups of the car. So before each night before testing, we go and set up the car. And by setup, I mean we go and measure our ride height and measure our camber and our toe and adjust it how we want it. And we keep track of all that to see, oh, the car was acting weird. Why is that? We can go back and look and see, oh, well, the toe was messed up or something like that. So this is just a picture of some of our data from I2. We have some damper data. We have our G-force, which kind of goes back to like lateral and longitudinal loads, brake pressures, speed, and pitch. So we have an accelerometer on the car, so we can kind of measure G-force as well as pitch and whatnot, and steering wheel angle. So we kind of look at what the driver was doing and hopefully look back at the data and see, oh, this is what the car was doing as well. This is why he was having issues. So, all right. So that's pretty much all I had to talk about for the presentation part. Thank you guys for coming. Are there any questions?
Is there a meeting on Sunday?
Yes. So I'm going to start holding suspension meetings on Sundays at the shop at 2 p.m. So that's right before the shop cleanup. So then you guys can help with the cleanup after that. But no, it's mostly so everyone's on the same page, so I can teach you guys. So we can all be on the same page with everything. And yeah, it's good to have meetings so you guys help you guys learn. What do you mean by parallel?
Like, are they like this or?
Yeah, they're not. You mean like parallel to the ground? Yeah, they're not quite parallel to the ground. They're like angled. It also depends on like how the suspension is moving. It changes as well. Any other questions?
So how do you decide the best camber for the car?
The best camber. So that goes back to the whole kinematic modeling and stuff. So we don't want too much camber. We also want some though, right? Because we're going into turns. So that all goes into like the whole process with kinematics, really. Kind of a lot to explain. So I'm also not the best at kinematics yet, I'm going to admit, but more of a structures kind of guy. So there's also a thing called camber gain. So as the suspension moves up and down, the camber can increase or decrease. So we don't want to just add a bunch of steady state camber, because then when our suspension moves vertically, then it could change. You have a lot more, and which is bad. You don't want too much camber. So yeah. Why is it bad? So it could lead to, for one thing, decreased contact patch. So grip, you want the most contact patch, which is where the rubber is touching the road. The section of the tire that's touching the road. If you have too much camber and you go into a turn, then technically the contact patch wouldn't flatten out to the road per se. So your contact patch is going to be smaller, and then you're going to have a lot of load on like a smaller section of your tire, which is going to lead to that section of the tire heating up a lot more and wearing prematurely. So if you see like if your car is like needs an alignment and there's something's broken on your suspension of your car, you look at your tires, you'll see like it's really worn on one spot and not worn on the other.
Well, why do you guys change tires when you do that?
You mean from like the big ones to the small ones? Okay. So that has an effect on, let me go back to, I'm not sure if there's even a slide up here about that. So we had, a few years ago, we had 13-inch wheels. We had run those pretty much since the existence of the team, except for maybe early on, they were probably slightly different. So we changed to smaller tires. There's a few reasons for that. So it affects our unsprung mass, which is unsprung mass is the weight of the car that's not on the springs. I mean, it's exactly what it sounds like, but so it makes the car lighter, essentially, for one. Secondly, it affects our yaw acceleration and how easily we're able to turn. So the tire is the farthest thing from the center of gravity of the car. So some basic physics, so like R cross F, the radius is far away from the center of gravity. So that means the force is highest there. So if we make that lighter, then there's less force there. So that makes the car rotate easier. Also makes us able to turn easier. So why do we want the car to rotate easily? If you think about this competition, and I know none of you have been to comp, but you'll see that in the events, there's not like big, giant sweeping turns. There are like really small, tight turns. And for that reason, we want the car to be able to rotate really easily and turn really easily. Again, this all starts getting into like all the dynamic stuff, but it is really interesting, but that's essentially why, to decrease weight and help us turn the car in tight turns.
How do you guys,
For the tire change, so that's just like pretty much basic hand calcs. Like you lose the weight, and then I should have included this slide here, but there is a document that has all of like the two-dimensional steady state stuff. That's like, it's all statics, forces and moments, and you can pretty much quantify it like right there, like that our yaw acceleration is going to be better. And then also like more of the base, like for like compound and whatnot. That also goes back to the tire data that we get. So you can see like we tested the bigger tires on this as well, and we can go through this whole process for compound and size a little bit as well.
when you guys do testing, what are like usually your like main concerns? Who's like the first thing you guys look for?
So in testing, I guess it depends on what we're testing, but let's just say like on a regular testing day, like we're not really testing suspension for performance. We'll bring the car in and give it like a visual inspection, make sure nothing's broken, and then look at the data and see if anything like looks off with the dampers. So that could indicate there's a problem somewhere on one of the corners. Just kind of look over the data and make sure that nothing bad is happening or nothing like weird, like anomalies in the data. If we're testing suspension, it really depends on what we're doing. So we're like kind of doing a mock autocross then. We'll like send the driver out there, tell him to try to go fast, and then have him come in, have him tell us what was going on with the car, like, or it was understeering or oversteering, and we'll try to make changes to that. So to change that, we can adjust our damper settings, and we can also adjust our roll bars and adjust the springs. So there's like a few different things that we can do to try and make changes to how the car is acting on track. Any other questions?
The benefits of using carbon suspension numbers over materials?
Good question. So we go back to our components. Jason was mentioning the control arms and push rods and pull rods are carbon fiber instead of some other material. So a lot of teams run steel. And our main reason for this goes back to weight. So carbon fiber, these control arms are about half as heavy as the steel ones, the steel alternative. Not only that, they're actually stiffer than the steel ones. So that sounds counterintuitive, like how could something be so much lighter but not stiff? And how is steel not as stiff, but it is. The carbon tubes are also stiff. So stiffness and weight would be the reason for that.
How does the aerodynamic package affect suspension?
So what do you mean, like in a, like how we package things, or like just high level, like what it does to the car?
I guess it's how it affects vehicle dynamics.
Okay. So aerodynamics, so why we put a wing on the car? This goes back to vertical load on the tires and tire grip. So tire grip is also a function of, as I showed on one of the slides, it's a function of your vertical load on the tire. So if we think about a wing, so airplanes fly, they generate lift. We flip the wing upside down, we generate downforce. Downforce pushes down on the car, and that's more vertical load on the car, right? So then we in turn get more grip on the tires, helps us go faster in the corners. Don't necessarily need as much in the straights, but in the corners we get more grip from the aero package. Anything else? Is that like what you're looking for? Like, yeah, okay. I mean, also like the under tray, we kind of, you know, our ride height isn't dictated by the under tray. It's more like them designing the under tray for the ride height. So the under tray is the portion of the aero package that goes under the car, and it utilizes ground effect to generate downforce as well. That's more of like an aero thing to talk about, but any other questions?
Why push rods in the rear that pull in front?
So that's another good question. So what he's talking about is the push and pull rods. This is a picture of the fronts. So the fronts are in pull, so that's the pull rod it connects to the top of the upright. So if you load on the tire, it's actually, you think about it, it's pulling on the rod. In the rear, the bell cranks and the damper are mounted up high, and then the rod is connected to the bottom of the upright, so then they're being pushed on. So one of the main things, I guess, to the reason for that is the difference between the two is it affects kind of like center of gravity location a little bit. So in the rears, like I said, the shocks and the dampers and the bell cranks are up high, so that's increases our center of gravity height a little bit. If you look at pictures of F20, which was a few years back, the fronts were pushed as well, and the dampers and the bell cranks were also like sticking at the top of the car, so that increases its center of gravity. It also kind of goes into like how you package things and how easy it is to work on. So push is generally easier to package. Not in this case for the front of the car because we just recently switched to the carbon fiber monocoque chassis. So we can't really, I guess we could like cut into the chassis and like mount the stuff, mount the bell cranks and dampers up high, but it's a lot harder to package.
How do you measure deflection or deformation in your members or at the mounting points?
At the mounting points, so like an inboard on the chassis.
Sure. Or how do you were talking about how nothing's a rigid body. So how do you measure how much they're not rigid bodies?
So I guess we could run FEA stuff to do that, but with information on torsional stiffness of the chassis, we can kind of estimate how much stuff is going to move around, I guess.
What about like the pull rods and push rods?
Like how much they would deflect?
Yeah. The members itself.
So yeah, I guess we could run that in ANSYS. Maybe do some like hand calculations on it. The control arms and pull rods and push rods have been an area of concern recently because they are bonded in, so you can't just weld carbon fiber. So like steel, you weld it together, it's fine, like it's not gonna fail. But these aluminum pieces are essentially glued into the carbon. We've been having issues with that failing, so one of the intentions this season is to look into that more and to like understand it better so they don't fail. Any other questions? No, we're good. All right, cool. Thanks again, guys, for coming. I really appreciate it. If you ever have any questions, if you ever have any questions, I try to be in the shop like every day. So usually later now than normal, so like after 7 o'clock or so. And like I said, suspension meeting Sundays at 2. So come out to those. Thanks again.
Why do a lot of the low transport?
Doesn't. So we get to stop.